How is the streaming looking? Like what? No sound? Or just, okay, it's going good. All right. Let's kick this off. Okay, so today's lecture is a bit of a mixed bag. So we're going to cover 3 different topics on which all fall under this sort of core computer science umbrella. So we'll talk a little bit about files, a little bit about practically how you can read-write files in Java, but mainly about the concepts behind them. Then talk about computational complexity, which, as I said before, we actually should probably have done a bit earlier because we've already mentioned quite a bit about complexity while we were discussing implementation of abstract data types. And finally wrap up with looking at formal grammars. All right. So, well, actually, I might start by throwing this question to you if anyone wants to answer. What is a file? Anyone has a concise definition? Yeah. Well, to be honest, I don't really have a precise definition or a formal definition, but let's just say when we talk about files in computer science, it's collections of data that are stored on what we call secondary storage or permanent storage. I mean, okay, technically we can have file systems that sit in volatile storage as well, so even that's not necessarily part of the definition. But we talk about, we mean things that are stored on hard drives or on your network file server or something like this, right? Now, the important thing about a file from our point of view is that a file consists of a sequence of bytes. Now, I'm sure you should know what a byte is. So a byte is an integer in the range 0 to 255. In other words, if you remember your powers of 2, it's an 8-bit integer, right? That's what a byte is. So all the data that is stored in files is just a sequence of bytes. Now, of course, you know there are many different types of files. We have source files that we compile into class files that get executed. We have program files that are part of the operating systems. We have images, sounds, video, documents in word processing documents and spreadsheets and whatnot, right? But all of this is just sequences of bytes as far as the file system is concerned. So it's up to the program that reads the file to interpret these bytes as the right kind of content. Now, most of the time you're not going to have to do all that by yourself. The standard libraries and in some cases the operating system might provide support for interpreting data as text or as images or as whatever it is, right? But part of that is that when you want to read a file, you kind of have to know what you are supposed to be reading, because sometimes you can open a file, look at the contents and guess what the contents are, but usually when you read a file you have an expectation about what to find in it, and you will interpret the contents according to what you expect it to be. Right. So when we deal with files in programs or in programming or computer systems in general, we often use the abstraction or analogy of a stream. And so what does a stream mean? Well, we said that a file is a sequence of bytes, and this means that when we read or write to a file or from a file, we do this sequentially. So we read a sequence of bytes, usually starting from the beginning and forwards until we get to the end or whatever stop condition we want. Now, in most file systems, you can also do random access, so you can find specific points in a file and sort of jump back and forth. But this notion of a stream of data is comes from the sort of old but still also current storage media that files are stored on. So I'll talk a little bit about it in a moment, but the types of things that we store files on, or at least used to store files on, are things that basically permit sequential access, which means that that's why we have this programming analogy of using it. Now, we also use this stream analogy or abstraction for other types of input-output in programs. So, for example, if you open a network connection to a server to read a web page, what you get is a stream, and you read bytes that are coming over the network connection. And same as with a file, it's then up to you to interpret these bytes as text that is HTML and then render it if that's what you want to do. Same with input from the keyboard. When you type on the keyboard, the characters that you type get put into a stream, which is accessible to the program that is running. We'll see some example of that a little bit towards the end of this segment. So, as I said, this stream analogy comes from the type of storage media that were originally used for files. So, quick poll. The thing up on how many of you recognize the thing on the left here? Know what it is? Right. A few hands. So I'm guessing the rest of you have not ever used a cassette tape to record or play music. No. So a cassette tape, or a tape in general, is simply it's a tape. It's a string of plastic ribbon with some sort of magnetic or metallic material glued onto it, and it stores information by using magnetism somehow. So you sort of can store a signal on this tape, and you can read then the signal by running the tape across a reader, right? And you can use that to record music or sound in general, but you can also use it to record data. And this was sort of, I think, one of, if not the earliest, one of the earliest types of secondary or permanent storage that was used in computers. So before you had permanent storage, you had only non-volatile storage, so basically memory in the computer. And all your inputs had to be typed in or read in from punch cards or whatever, and your outputs would come out on printers or screens or something. But before that, you didn't have any sort of permanent place to store data. So, of course, old tape machines were big and clunky, but they've evolved over time, and I think the rightmost picture is showing some reasonably modern data storage tapes and drives. So these are sort of small cassettes with tape in, and they can store quite large quantities of data. So I'm not sure exactly what the capacity of the things that are being shown here is, but read recently that the sort of theoretical limits for the most recent generation of tape storage is on the order of some few hundreds of terabytes on a cassette like this. So so although it's a very kind of old-fashioned technology in a way, it is still in use, and the reason why it's still in use is because compared to everything else that you could store data on, tape is cheap, right? You can get a lot of data onto a small piece of tape, and it doesn't cost very much. So they are extensively used for things like storing data that you're very unlikely to want to see again, but still want to store. So basically backups. Right. If you want to back up a large quantity of data, you use tape to do it. hopefully you're never going to have to read your backup, because you only need to read it if your system crashes or your disk breaks or something like this. But it's good to have. So if you want to record lots of stuff and keep it safe, then tape is a good solution for that, and it's still very much in use. Now, if you sort of understand how the tape works, you see where this sequential reading comes from, right? Because in order to read something off a tape, well, you first have to sort of find the right position to start. So you have to fast forward or fast reverse the tape to the right position, and then because you read by running the tape across a read head, that means you are reading things sequentially. If you want to jump back and forth around in the tape, you can do a lot of spooling back and forth, a lot of fast forward and fast backward or reverse. Now, the other thing that you probably have heard of is hard drives, but who recognizes the thing on the left there? Do you know what that is? Interesting. A few more people have seen this, at least. Yeah, so that's a gramophone player. So again, it's an old, in fact older than the cassette tape, form of recording and playing music or other sound. So the gramophone player plays, or the sound here is stored on a disc, right? So the disc rotates. On the disc there's tracks, or a track. Actually, it's a long spiraling track on the disc, and the read head, which is the little arm there, follows the track and reads sort of vibrations from the shape of the track, and that gets translated into a signal, which gets translated into sound. And hard drives work in a very similar fashion. So if you open up a hard drive and look inside, it's got a disk in there. That's why we call it writing to disk, or saving stuff on disk. And it's got an arm, and that arm sort of can move back and forth, and the disk spins around, and it does the same thing. It reads data sort of that passes sequentially under the head of the arm as the disk spins around. So compared to the tape, it's a bit faster to jump around here, right? Because if you want to jump from one track to the next, you don't have to sort of wind your way all the way into the next track. You can just pick up the arm, move it a little bit, and then put it down in the right place. So in that way, the disk has a much faster random access time than the tape. But still, and we'll talk about this later, compared to memory in a computer, the access times here are pretty slow, because you still need to do something mechanical here. You need to actually physically lift up the arm, move it, and put it down, right? And then you need to wait for the disk to spin around to get to the sector of the disk that you want to read. But again, similar to tape, once you have found the right starting place, then you can read a sequence of bytes by just sort of spinning the disk along, right? So again, it has this characteristic that finding a specific place takes time, but once you've found a place, reading sequentially all the bytes that come after that point doesn't take much time compared to the time it took to get to that point. Alright, so let's look at how this reading looks in Java if you want to read files. So as said, the analogy or abstraction that we use for file is a stream, and it's used for many things other than files, also in Java. So in Java you have a package called java.io, which contains a number of different stream implementations. So you have input stream, output stream. Input stream is for reading, output stream is for writing, and you have specialized subclasses of streams for different purposes. So you have file streams for reading and writing files. You have network streams for reading and writing from network connections. They're in different package, but and you can have streams for reading from data structures in memory and from pipes and all kinds of things. So to read a file, we open the stream, or create a stream object which opens the stream, and then we read or write bytes. Generally we have to put try-catch around this, because all sort of I/O operations in Java can raise an I/O error, which we should catch. And finally, we should make sure that we always close the stream when we're done with it. We'll say a little bit more about why we should close. One reason is just that it's good practice, good housekeeping. Always close your streams or close your files when you're reading or writing. But in particular, when you're writing, it's important that you close the stream, because otherwise you might lose some data. So let's have a look at, let's have a look at doing this. So here is so here we just create a file input stream from a text file. Skip here is just skipping the first 959 bytes because I wanted to get to the interesting part of the text. And then we're just going to read a bunch of bytes from this stream here. So we're calling a little function here that I wrote called show bytes. So let's have a look at what does show bytes do. So show bytes takes an input stream and a number of bytes that we want to show, and it reads from this input stream. So here's the crucial part. So we read from the input stream by calling read. Now, I said we read bytes from a stream, so a stream is a sequence of bytes. But actually in Java, the read method of an input stream returns an int, not a byte. And the reason why it does that is because it needs to use a value that is outside the range of possible values to indicate that you have reached the end of the file. So, in fact, let's look at the API documentation just to have a look at what you can do with the stream. And we have our input stream. Right. So, as I said, you have the read method here, which says reads the next byte of data from the input stream, right? And it returns, I think it returns -1. If no byte is available because the end of the stream has been reached, the value of -1 is returned. There are also a couple of other methods. You can provide a byte array as a buffer, and then tell it to read a certain number of bytes, and it will read as many bytes as it can into that up to the limit you specified. Or if the stream ends before you have read that many, it will return a number that is the number of bytes that it actually read. So that's a kind of a standard interface method for stream reading, which you will find in other standard libraries as well. If you go to C programming, for example, you'll typically have a read method that looks something like this. You provide an array to read into, you specify how much you want to read, and then the function or method returns the number actually read. Right, that's not the one we wanted here. So here we just read 1 byte at a time. We put them into an array, and then there's a little bit of stuff here which will just nicely format the output, the stuff that we have read, so that we can see it, and then we just print it. So going back to the main here, we're just going to read 16 bytes at a time, because 16 is a power of 2, and it happens to fit sort of reasonably well on the screen and show those bytes. So let's run that. And see what comes up. So here we have on the left we have the hexadecimal encoding of the bytes read. So not sure how well you can read hexadecimal. So for example, you can see here, so 20 in hexadecimal is 2 times 16, so it's 32, right? And on the right here, I've just shown the character corresponding to that byte for those characters that are within what we call the printable character or the printable ASCII range. So character numbers between 32 up to 127 or 26 is what's usually called the printable ASCII range. So those correspond to sort of things that look like characters, and then we just put a dot for all the other things. So just to show you what we're looking at, actually maybe a good idea. So this is what we're reading, and as I said, we skipped the intro, so we start reading from this point here, from this line. So this is the story of Snow White translated into Icelandic. And why did I pick that example to show you? Because I wanted to illustrate the point at the beginning here, that the data, if we just read it, is a sequence of bytes. And it's up to the program that reads it to interpret this as whatever it is we actually want to read. So in this case, the contents of the file is text. But as we could see here, when we look at the output, where's the output? There. It's not that straightforward because we don't sort of have a one-to-one correspondence here between byte and character. Some bytes correspond to printable characters, some don't. And the reason why is that when we encode, when we store text in a file, we need to use some kind of encoding, right? So we need to specify how does text get translated into bytes. And then when we read bytes, if we want to interpret them as text, we have to use this encoding or decoding the encoding in order to turn the bytes into text. And the basic idea of all text encoding systems, or really all data encoding systems, is that everything is assigned, everything is a number, right? So if we encode text, then every character that we want to be able to represent is represented by a number. Now most, I guess, modern sort of computing systems would be using Unicode, which is a system for, or a standard, I guess we can call it, for encoding characters as numbers. So Unicode defines this number, which in Unicode is called a code point, for somewhere around 120,000 different characters. So that's not just sort of the English alphabet, it's all kinds of alphabets that are in use in writing today, and a few historical ones, and I believe also a couple of fictional ones are in there as well. I'm not sure if there's Unicode numbers for Klingon, for example, but there may very well be. So the Unicode standard has a space for a very large number of different code points. It's somewhere in the excess of 1 million. But the Unicode standard only does sort of the first part of the job, which is defining this correspondence between character and number. So for example, it says that code point 69 is the capital E, the Latin capital E. That's what it is. Okay. So that's all it says. So it doesn't actually say how that gets translated into bytes. So there's another component here which is called an encoding, which is a system for mapping between sequences of bytes and these code point numbers. And a simple encoding would just be that we have a fixed size of numbers. So let's say if we I mentioned before ASCII. ASCII is an older standard for encoding text, which uses just a single byte for each character, which means that you have or in fact it doesn't even use a single byte, it uses 7 bits, really basic ASCII. So that means you have only 127 possible characters, which is enough if you just want to write English, because you can do your capital letters and your lowercase letters and a couple of punctuation marks and quite a few other things with 127 different characters, but it's not enough for Unicode. So old formats like ASCII have a very simple encoding scheme, which is just a one-to-one correspondence between byte and number. But if you want to represent bigger things, then you might need a more complex encoding scheme. So one that is sort of commonly used is the UTF. There's UTF-8 and UTF-16, depending on the character width. But these are a little bit complicated because they're variable length. So the UTF encoding says that code point 69 is encoded with just 1 byte, whereas code point 8364, which is according to Unicode the euro currency sign, is encoded using 3 bytes. So when you read a file that contains UTF encoded Unicode text, you need sort of a decoder that understands this encoding and maps this sequence of bytes that we're reading into a sequence of numbers, which are the code points. Now, the other next step of the process here, which also Unicode does not specify, is what does a capital E look like? So Unicode is just a standard that says that code point 69 is a Latin capital E. It doesn't tell you what a Latin capital E looks like. And I'm sure you've heard about fonts. If you've done anything with Word documents or something like this, you can change your font. And that's sort of the job of the font, right? Is to turn this character into something that is visible. So you can have your capital E look in a lot of different ways. But as long as it looks like something that we can recognize as a capital E. Alright, so this is a fairly complex process, but like I said, standard libraries in programming languages provide support for this. So in Java, there are things called character streams, or actually they're called reader and writer, which are classes that take a stream, a byte stream, and convert it into a character stream, which means that instead of reading and writing bytes, we read and write characters. So all of this machinery of dealing with the text encoding is encapsulated in these reader-writer classes. So similar to the input-output streams, reader and writer are sort of abstract or generic classes. Not generic, I shouldn't say that because they're not generics. They're abstract classes. They have different concrete implementations which work on different types of streams. So there's an input stream reader and an output stream writer which work on input and output streams. There's also specialized subclasses file reader and file writer which work directly on files if you want to use those. So let's look at what we get out of this if we try to use these instead. So here, just to show what we're doing, so same as before, we open the file, create a file input stream, but we also wrap this input stream in a input stream reader. So that means we get a reader out here. And instead of calling show bytes, we'll call show chars. So show characters. And show characters takes the reader rather than the stream as an argument. So let's have a quick look at what that one does before we run it. So similar to show bytes, what this one will do is, the main thing it will do is to read one at a time a number of characters from this character stream and put them into an array, and then we'll just print that array of characters as a string, and we'll also translate all of those characters into their code points and show those alongside the actual text. So let's try that, and again on the same example. So so if we scroll back up here, we can see this is the actual text. These are the characters that we read from the file, and in brackets here we have the sequence of code points. So now I don't know exactly how to pronounce this, but what you can see is that we have some non-standard characters here, because this is written in Icelandic, which uses a number of characters that are not in the Latin alphabet. And those characters have code points that fall outside of this sort of simple single byte character range. So 222 and 240 and so on. All right, where are we up to? All right, so that's a little bit about text encoding and about reading reading and writing files in Java. Want to say two more things about files, or file reading and writing. So I mentioned before when I talked about the different storage media that the problem we have with these is, or if you want to call it a problem, is access time. And to quantify this, these are some numbers from that got from the previous lecture of the course, but let's just look at, say, the difference between disk and RAM. So RAM, random access memory, is just the memory of the computer. Disk is a standard hard drive, right? So reading, or rather finding a specific byte in memory might take you about 10 nanoseconds or something like this. Finding a specific byte on disk might take about 10 milliseconds. So that's a difference of 10 to the power of 6, right? If I remember my units correctly. So it's a difference in speed on the order of 1,000,000, right? So reading from a disk, or finding a specific byte on disk, is 1,000,000 times slower than getting a specific byte out of memory. But as I mentioned, because at least on traditional media like tape and disk, reading a consecutive block of bytes is not much slower than just reading the first one out of the block. So once the expensive part of the process generally is finding the right spot to read. And once you're there, you can read a whole chunk with not much overhead compared to just reading one byte. So because of that, it makes sense to use buffering. So what does buffering mean? Buffering means that instead of reading just one byte off the disk or the tape or whatever it is, when we read something, we read a whole chunk and we put it in memory. And then if we want to sequentially read bytes, we read them out of that buffer in memory until we get to the end of the buffer, and then we have to go and read the next chunk and put that in memory. And that speeds up your operations quite a bit, because instead of doing a disk access every time you read a byte. You only have to do it every so often when you need to refresh the buffer. So in order to sort of illustrate the difference, let's have a look at another example. So here's a little program, and what it does is opens a file input stream for a text file, and it opens a file output stream for another text file. And then, so remember that I said the -1, the read method returns -1 to indicate end of file. So here we have a little loop that just reads 1 byte at a time from the file, the input file, until it gets to the end, and writes every byte to the output file. So essentially we're just copying the contents of the input file to the output file 1 byte at a time, right? And just counting how many bytes we have copied and how long, measuring how long it takes. So let's run that and see what happens. So we copied, what was that, about 180,000 bytes, and that took us about 0.3 seconds. Right. Now this is doing this without any buffering. So Java file streams by default are non-buffered. So if you want to use buffering, you have to tell it to use buffering. So this is a bit different from, I think, in many other modern programming languages, you get buffered file I/O by default, and if you want to have non-buffered, you have to say non-buffered. But in Java, you get non-buffered by default, and if you want to use buffering, you have to wrap your reader or stream in a buffered reader or I think there's a buffered stream as well. So the Java I/O package provides these buffered reader and buffered writer, which you can wrap around a reader or writer to provide buffering. So let's try that on here. So if we want to use buffering, then we create a buffered input. We're actually using an input stream, not a writer or reader or writer here. So a buffered input stream and a buffered output stream around the file input stream and file output stream. Right. And we can specify a buffer size. Here we have set the buffer size to 1, which is not a particularly good value, but we'll do that just to see what happens. So we run that again, and we see that it took about the same amount of time. Actually, it took slightly longer, so about 0.3 something seconds. But that's because we're not really doing any buffering here. We just read 1 byte at a time into the buffer, and in fact it took a little bit longer because we have this overhead of buffering and then reading from the buffer. So let's see what happens if we actually put a buffer that we can make some use of, and we're not even going to make it very big. Let's say, again, we like powers of 2, so let's use a buffer of 16 bytes and run this again. And you can see that the time here has dropped by almost an order of magnitude, right? So we've gone from 0.3 something seconds to 0.04 seconds. And now this is a pretty small text file. It's just, well, it's about 180K. If it was something bigger, we would probably see a much more dramatic difference. Now, I'm not sure if this is entirely linear. We can try and make this a bit bigger. Let's say we go to something like 1024, be a reasonable standard buffer size, and run that. Okay, so that didn't really give us an order of magnitude improvement, but still it made the it run yet a little bit faster. So this just illustrates this fact that sort of 1 byte at a time unbuffered reading from disk is very slow compared to reading from memory, which is what we do if we're doing buffered access. All right, I think we spent quite a bit of time on this. So just the last thing I want to say about I/O and streams. So I mentioned before that we use these streams not only for files. Streams are a very common abstraction. We use them for essentially all I/O, at least in Java it does. So including I/O from the terminal. So you've probably used system out print line every now and then to write out debug messages or something from your code, or even some of the homework exercises and exam problems have specified that you should write something to system out. And system out is a stream. It is an output stream. It's a character stream. So same as writing to a file, writing to system out produces an output stream of characters which get shown on the terminal. And you also have two other streams, which is system in and system err. So system in is your input stream. This is if you're typing input on the keyboard and you want to read it in your Java program, you read it from system in. And the error stream is also an output stream, so it will kind of go to the same place as the output stream. And generally the difference between the standard output and standard error stream is just that the error stream is not buffered. The output stream is by default buffered. Typically the behavior of a terminal is that things that get printed to the output stream will only be printed once the line is complete. So when you get a new line, whereas things that get printed to error get printed immediately. So that's why, and that's because we use the error stream for error messages that we want to see immediately, and we use the output stream for normal output. Now, having these free streams, this is a sort of standard feature of the sort of Unix, POSIX, Linux type operating systems. I'm not sure if it's common to all operating systems having these free streams, but at least having an input and an output stream is probably common to all, and you would probably find some mechanism for accessing those streams on all operating systems. All right, so that's it about files, and the next topic, as I said, we want to go through today is computational complexity. And I'm going to actually I'm going to go publish there. So I'm going to try doing a mini quiz today, but I will give you a bit of time to think about it. So hopefully you should now be able to see the mini quiz question. You don't have to answer it straight away, but have a think about the question while we're going through this material on computational complexity, and then we'll see what answers we have by the time we get to the end of it. All right, so when we talk about complexity of an algorithm, we use the term a little bit sloppily. Sometimes we mean, oh, this is a complicated algorithm, it's difficult to understand, it's difficult to implement. But when we talk about computational complexity, what we mean is the computational resources that this algorithm will use in order to solve a problem. And specifically, it's the resources as a function of the size of the input. And usually we talk about the worst case complexity, which is the sort of resources that the algorithm will use for a given size of input for the worst possible input of that size. But sometimes we also talk about average complexity or amortized complexity or something like this. So we can have different notions of what conditions we're measuring this resource usage under, right? So what are the computational resources that we talk about here? Well, the the most obvious one is time. So how long will it take the algorithm to execute? And when we talk about time, what we're really talking about is counting some sort of elementary operations. So we're not really concerned about does it take this many milliseconds or that many milliseconds. I mean, in some contexts we are. But when we talk about algorithm complexity, it is sort of independent of actual implementation, actual hardware, and so on. So what we're interested in is how many steps does the algorithm need to do for some notion of what is a step. Right. Another thing that we might measure, or another resource we might look at, is memory. So how much memory does the algorithm use? And again, we're not necessarily talking about bytes, but about how many elements of some primitive size or some primitive type of elements does the algorithm need to keep in memory. Right. But there's lots of other measures or resources that we could measure. So one that's sort of more recently become interesting is energy. So that's because the computers consume a lot of power, a lot of electricity, and if you're running very big computers doing lots of work, then that's significant. And sometimes you can sort of reduce the amount of energy that computers use by changing the way the algorithms work, because different types of operations can have different energy requirements. So fetching data from memory is different from executing operations on data on the CPU and so on. In some more specific instances, so for example, if we talk about distributed algorithms, we might be interested in communication complexity, which is how much communication do the different distributed parts of an algorithm need to do, again, in the worst case, in order to actually successfully solve their problem. So we might think that an algorithm that needs less communication is better than the one that needs more, because either communication is slow or it's expensive or whatever, some reason. Same with I/O. If we talk about algorithms that operate on data that is stored on external storage, like disk, we might measure the number of I/O operations. And again, it's the same idea that we're looking at how many in the worst case as a function of the size of the input. In machine learning, we sometimes talk about sample complexity, which is the notion of how many samples, how many training samples does a learning algorithm need to converge to a sort of a learned result with a certain reliability. And again, you can have bounds on, depending on the algorithm, on upper and lower bounds on saying that it needs at least this many samples, or if it gets that many, it's guaranteed to reach a certain performance. So algorithm complexity is important because it's one of the things that we use to distinguish between different algorithms, between what is a good algorithm and what is a bad algorithm. And it's important, especially time and memory complexity is important when we solve large problems, because if we have an algorithm that scales up badly with the size of the input, it might be fine for solving small problems because the difference is so small that we don't notice it. But when you try to solve really large problems, it becomes sort of a bottleneck. It will just take too long to run. So we usually express complexity using what's called a big O notation. So I don't know, how many of you have seen big O before? Yeah, quite a few. You covered it in 1100, right? Yeah. And I don't know if any of you have gone through 1700, but again, or 6700, we cover it there as well. So just quickly to recap, so big O is sort of a way of simplifying functions. So I like to read it as on the order of. So if we say that a function g of n belongs to big O of f of n, or you can say is on the order of f of n, what it means is that for sufficiently large values of n, g of n will behave about the same as f of n, or it will trend in the same way. the precise definition is that for some constant n0, for all values larger than that, the function g of n is upper bounded by a constant times f of n. But the example here is showing, so here we have function g of n, which does some some squiggliness, and f of n here is just a line, so it's a straight line. We have f of n equals n there, and we have f of n equals free n, and what we can see here is that for some sufficiently large value of n, the function g of n is upper bounded by 3 times n. So that means we can say that g of n is on the order of linear, is what we would usually say. So it behaves the same as a straight line for sufficiently large values. And that's kind of the takeaway from that. That's what we want to say with this. And we use this to characterize the complexity of algorithms as a function of the size of the input. So I was going to step through a couple of small examples here, just to show how we think about complexity of algorithms, specifically about time complexity. So in the analysis of time complexity, as I said, we're counting some sort of elementary operations, so we're not measuring actual time. Generally, we say that simple statements in a programming language are constant time. But, and remember that we have this constant factor c in the f of order f of n, so we don't really care if it takes, if we do 2 statements or 5 statements, doesn't make a difference, it's constant. But we should be cautious when we're counting statements or things like this, because something that looks like just a simple statement in a programming language may in fact be a call to a library function that does something very complex, right? So we have to be a little bit cautious about what we count. All right, so just to illustrate the concept here, let's step through an example. So we have a problem here. Our problem is to find the greatest element that is less than or equal to x in an unsorted sequence of n elements. And we're just going to assume here that there is at least one element in there, just so we don't have to worry about what we have to do if there's none. So how would you solve this? Well, you have 2 solutions right there. So we could just search the unsorted sequence, find all elements that are less than or equal to x, and find the greatest one of them. Or if we have a sorted sequence, we can do a more efficient finding of the greatest element that is less than or equal to x. But because we don't have a sorted sequence, we have to sort it first. So we could sort it and then do a sorted find. So we have 2 different algorithm ideas. So let's look at what is their time complexity and how does it compare. So here's just a simple implementation of the unsorted find. In fact, this is even specifies that the input is integer, not just any element. So it's a simple loop. We just go through all the elements of the list. If we find an element that is equal to x, we just return straight away, because there cannot be something that is less than or equal to x and greater than x. So if we have found that x is in the sequence, then yeah, that must be the answer. Otherwise, we just check for everything if it's less than or equal to x, if it's better than the current best. Actually, hang on, that should be, isn't that the wrong way around? That should be a greater than, not a less than. Okay, yeah, this one here should be greater than, not less than, because we want to find the greatest one that is less than or equal to x. So sorry, there's an error in the slide there. So we keep track of our current best. If we find one that is less than or equal to x, greater than the current best, then we just record that as our current best, and at the end we return the best. Okay, So let's look at the analysis. And here we're just going to count comparisons, because that's kind of a good indicator of the amount of work being done here. We're not really doing much else in this algorithm. We're just looping, so we're just doing comparisons. And the rest is just looping and assignments. So if we're really lucky, well, the first element of the list is equal to x, and we're done immediately, right? But that's not the worst case. That's the best case. So in the worst case would be that we have something like a list where every element is less than or equal to x, but every element that we find is better than the previous best. So that means we're going to sort of be going through the whole list and comparing every element with x and comparing it with the current best. So that means we're doing about twice the length of the list number of comparisons, which gives us in big O a order of n complexity. So the time it will take to do this will sort of scale linearly with the size of the list. This is, of course, assuming that, again, we counted comparisons. So this is assuming that comparisons are constant time, which would be okay for an okay assumption for integers. If we were comparing something more complex, then perhaps not. Perhaps comparisons could have very different time complexity for different elements if we were comparing complex objects of some sort. But for this case, it's a reasonable assumption to say that they're constant time. And this is taken from an older lecture, so it's not a Java implementation. This is an implementation in a different language, but this is measured runtime for running this averaged measured runtime for running this algorithm on lists of sort of 100,000, 200,000, up to 500,000 elements, and or you can't even see there are some breaks in the line. It's not actually a perfectly straight line because there is some noise just in the measurement of CPU times, but it looks pretty much like a straight line. So this really has linear time complexity. All right. So our second algorithm was that we sort the list first, or sequence, and then we find the biggest element that is less than or equal to x in a sorted sequence, right, or sorted list. So how do we find things in a sorted list? Well, I think you probably have encountered this idea a couple of times before. You do some kind of bisection. So we look at sort of the element in the middle of the list, and we see, is it greater or smaller than the one we're looking for, and then depending on that we either look at the left half or the right half. Right. So well, the first thing here is just checking if the last element is less than again, I think that should say less than or equal to x, not less than. Then if the last element in the sequence is less than or equal to x, well, then that last element must be the answer, because it's the biggest one in the sequence, right? So that's just taking care of an edge case. And otherwise we sort of maintain a actually, and there's a few more. No, that's okay. So we maintain this sort of interval defined by the lower and upper index. So the lower index is the index of a value in the list that is less than or equal to x, and the upper index is the index of a value in the list that is greater than x, which means that we know that x, if it exists, is somewhere in between these two indices, and then the greatest value that is less than or equal to x is also somewhere in between there, right? And then we just find whatever is in the middle of them and get that number out, and we compare that to x. If it's less than or equal, then the answer we're looking for is in the left half, so between lower and I've done this wrong again. Oh no, sorry, it's in the right half. Yeah. So between that midpoint and upper, so we move the lower end of the interval up. And if that middle point is greater than x, that means the answer we're looking for is in the left half. So we move the upper end of the interval down. Right. And once that interval has shrunk to size 1, so lower and upper are right next to each other, then because of this invariant property, we know that the value at index lower is the answer we're looking for. It's the greatest element that is less than or equal to x. So here again we're doing a loop, and and again, if we want to sort of count comparisons, we're doing one comparison every time we go around the loop. We do a little bit of arithmetic as well, but we can say that calculating the average and indexing the list is probably about the same complexity as the comparison, or even less actually. So the key question is, how many times are we going to go around the loop in the worst case? And of course, like all bisection algorithms or things like this, the idea here is that every time we go around the loop, we halve the size of the interval, right? We start out with the whole list, and then we take the middle, and we're only going to look at one of the two halves. And we keep doing that. So we keep cutting this interval in half every time we go around the loop. And if we have n values to begin with, we can do this at most log 2 of n times before the difference between upper and lower is 1 or less than 1. So that means we get a complexity which is on the order of the base 2 logarithm of the size of the list. So that looks good. We have sort of a much faster way of finding this element we're looking for in a sorted list. But our algorithm, our second choice of algorithm was to first sort the list because it's unsorted, and then do a find in the sorted list. Oh, this is just again measured runtime for this sorted find algorithm, and again you can sort of see that it looks like a logarithmic curve. Again here we're also, if you look carefully, you can see we're using much bigger values here than we did before. For the linear one, we're using up to 500,000 elements, and that took something slightly more than 0.1 second. Here we're sort of almost starting at 500,000 elements, and that's taking somewhere on the order of 0.00002 seconds. And then quadrupling that is just adding something like 0.00002 to the number. So yeah, logarithmic functions generally are a lot faster than linear. But the problem is that we haven't accounted for the sorting, right? Now, if we wanted to sort a list, we would just use maybe the Java standard library has sort methods for lists, but how fast can we sort? So we don't know exactly how that's implemented, but let's say that we might use the standard implementation of sort in Java, or we might use the best possible implementation of sorting. So the question is, how fast can you sort? What is the best possible implementation of sorting? So in order to answer this question, we have to look at the problem complexity rather than the algorithm complexity. So what is the complexity of sorting? We can talk about the complexity of different sorting algorithms, but we can also talk about the complexity of sorting. And when we talk about the complexity of a computational problem, what we mean is the sort of the same as an algorithm complexity, but the complexity of the best possible algorithm according to that complexity measure. So if we talk about time complexity, then what is the sort of the smallest, the algorithm that solves this problem that has the smallest time complexity? Or the computational resources that any algorithm that solves the problem must use, right? And just as a little aside, I don't know if you have, some of you might have taken or might be concurrently taking the Foundations of Computing or Theory of Computing course. I don't know if you discussed the hierarchy theorem in that, but there's essentially a theorem that's saying that for any function, you can define a computational problem whose complexity will be on the order of that function. So we can always invent problems that are arbitrarily complex for both time and memory. So to the question again, how fast can we sort? And there is a sort of well-known result that any sorting algorithm that only uses pairwise comparisons of elements must, in the worst case, do at least n times log n comparisons in order to sort a given input of size n. Right. And the argument for this is sort of that you can look at what a sorting algorithm does is that it selects a permutation. So if we have an input of n elements, we know we have n factorial possible permutations, right? And in order to sort the sequence, what we have to do is select the right permutation and then apply that permutation to the sequence. So whenever we have an unsorted sequence, you can think that, well, there is a particular permutation that will permute this sequence into its sorted sequence. If there is non-unique elements, it could be more than one. But let's sort of ignore that a little bit and just say that. So for example, if we have just a list of length 3, if the input is just already sorted 1, 2, 3, then the permutation that will turn this into a sorted list is the identity permutation, right? Which doesn't move anything. If we have the input, say 2, 3, 1, then the permutation that will turn this into a sorted sequence is sort of a cyclic shift to the right, where the last element moves first and the other two move back one step, right? So for every input, there is a particular permutation that is the right answer in some sense. Now, so that's the first part of the argument. The second part is that, well, if the sorting algorithm only does pairwise comparisons, what can you do when you do a pairwise comparison, right? So think about you're doing a pairwise comparison, x is less than or equal to y. What can you do with that? You can do an if, right? Either x is less than or equal to y and you do something, or it's not and you do something else. So every time that the sorting algorithm does a comparison, it can make a decision. It can go either one way or the other. But it can't go 3 different ways, because the outcome of the comparison is just either yes or no. So every comparison that the sorting algorithm makes results in a 2-outcome decision. Either does this or does that. So if we think of all sort of possible executions of a sorting algorithm, we can draw them as a binary tree, where it makes a comparison and it chooses either one outcome or the other, right? So all the possible executions must end with a permutation, right? Because we said before that the right answer to a sorting problem is to select the right permutation. So we have this kind of binary tree where we have n factorial possible right answers at the bottom, and every time that the sorting algorithm makes a decision, it sort of selects either one half or the other half of the remaining possible choices, right? So then, of course, we know that the height of a binary tree is base 2 logarithm of the number of leaves if it's complete. So and the height of this tree is the number of comparisons that the sorting algorithm needs to make. So the worst case execution of the sorting algorithm will be the longest path from the beginning down to a leaf node, which is where it has finally selected a correct permutation, right? And it has to be able to output every possible permutation, because otherwise there would be some input for which it doesn't output the right permutation. So that means that the worst case is then base 2 logarithm of n factorial, and then you can do some algebra on that and work out that for sufficiently large n, that's lower bounded by n log n. Right. So that's how we get the result that in the worst case, any sorting algorithm that uses only comparisons will have to do n log n comparisons to sort a sequence of length n. So putting this sort of all together, well, here's again just measured runtime for sorting, and so this is using a standard library implementation of a good sorting algorithm which achieves n log n complexity. You can also do bad sorting algorithms which have a higher complexity. Sometimes they're not, I shouldn't call them bad, because in some cases it's actually justified to use them. But if you're sorting small sequences, it might be better to use an algorithm that actually has a worst case complexity for large numbers, but still behaves better on small inputs. But this is, here we're sorting sort of, and again, if you look carefully, you can see that the range of sizes here is a bit different. Here we're dealing with sort of 10,000 up to 60,000 elements in a list or a sequence, and you can, the dotted line is just a straight line for comparison, so you can see that this is sort of trending up a little bit faster than a straight line. It's a bit difficult to see otherwise, but this is the n log n factor, or the log n factor in n log n. So sort of putting all of this together, the outcome is that our second algorithm is worse than our first, right? Because the first algorithm has a sort of linear time complexity. The second algorithm has to do first a sort, which is n log n, and then the sorted find, and the sorted find is only log n, but the total time will be dominated by this n log n factor, right? So the sorting will always take much longer than the finding in the sorted list, and the sorting is slower than finding in the unsorted list. So this is just illustrating this using sort of rate of growth. So if we take the time that it takes to apply an algorithm to an input of twice the size and divide that by twice the time it would take to apply it to an input of size n. So if you have, I guess that formula is a little bit, it's a little bit tricky to interpret, but if you have a linear algorithm, you would expect this ratio to be 1, right? Because it's just saying that if the algorithm is linear, then the time it takes to do something that is twice as big is twice the time it took you to do something that's n. And what you can see is that unsorted find is pretty much a straight line here around 1. So it is what you expect it to be. Sorting, on the other hand, because it's above linear, you can see that it's trending up. And so that means not only is the ratio here above 1, but it actually increases as the size increases. So every time we double the size of the input, we pay a bigger and bigger price for doubling it, for doing, and that's the n times log n factor. For the sorted find, on the other hand, we have sort of the opposite behavior. First, the ratio here is less than 1, so doubling the size of the input does not double the time, it does less than double the time, and in fact there's even sort of a downwards trend here. It's kind of difficult to see, but every time we double the input size, we pay less of an overhead than the last doubling, and that's the log n complexity. All right. So before we wrap that segment, let's go and have a look at this quiz. Now, can we see quiz results? Okay, that's interesting. Okay, so let's talk about this question a little bit. So the question is, what is the worst case complexity of finding the smallest difference between any pair of elements in a list of numbers? And the majority answer so far is n square, which is a reasonable answer, because in general, if you think about doing anything that involves looking at every pair of something, right, you would be expecting this to be n square. If you go, we have to take every number in the list and compare it with every other number in the list. So that's a quadratic number of pairs, and we have to compare them for the difference and find the smallest difference. However, we don't have to do that, because again, this is asking about the complexity of a problem, not an algorithm. So it's asking, what is the complexity of the best possible algorithm for solving this problem? So, although the simple approach here is to just compare all elements pairwise, there could be a better algorithm that gets us the right answer. And in this case, I would say that there is. Because we're talking about a sequence of numbers, or a list of numbers, and we want to find the smallest difference between any pair of numbers, right? So if the sequence was sorted, then the smallest difference would be the difference between some consecutive pair of elements, right? Because obviously if we have two non-consecutive elements, there will be a smaller difference by taking the difference between one of them and something that's in between. So if we sort the list first, then we can find the smallest difference by just linearly looking at every pair of consecutive elements. And we know that we can sort a list in n log n. So I would say that the complexity should be about n log n. And in fact, we could even potentially, because we have been a bit specific here and said that this is a list of numbers. So, and our lower bound on sorting was for sorting algorithms that only use pairwise comparisons. Now, if we're sorting numbers, maybe we can do something smarter than just looking at pairwise comparisons. And in fact, there are things like what's called radix or radix sort and or bucket sort and things like this. So where we could go, well, we take our numbers and we just look at the sort of, we bucket them by size of number, like magnitude. So we put all the ones that are tens in one bucket, all the hundreds in one bucket, and all the thousands in another one, and then we just have to sort each bucket because we know that all the thousands are going to be bigger than all the hundreds, which are going to be bigger than all the tens. Or we could then look at, in each bucket, we can look at what is the first digit, because we know that all the ones that are the same number of digits and start with a 2 are going to be bigger than ones that start with a 1, and so on. So I'm not sure if any of that is actually going to get us a better complexity than n log n in the end, but at least because the problem is a little bit more specific, it means that there are possibilities for perhaps doing better. But at least we should be able to make n log n for this problem. All right, so to finish off the part about computational complexity, I want to give you a famous quote. I don't know how many people have heard this quote. Very often it's misquoted and the last two words are left out, which makes it slightly less true. This guy, I don't know what his initial stands for, Hoare, famous in theory of computing, invented a system of logic for reasoning about program correctness. But he is supposedly said that premature optimization is the root of all evil in programming. So it's not the root of all evil in the world, but at least in programming. And the message here is that, yes, complexity, especially time complexity, is very important if you're solving large-scale problems. Or if you're solving perhaps not so large-scale problems, but you have to solve a lot of them. Or you have to run something that has to run very often, or run in a time-constrained environment, or something like this. But trying to optimize every single algorithm for maximum efficiency is a waste of time, and potentially it wastes your time, because trying to make the algorithm as efficient as possible takes up more of your time. And if the difference between sort of your maximum efficiency algorithm and just a straightforward implementation is a couple of fractions of a second on something that you're going to run once or twice, it makes no difference, right? Even if you're going to run it a lot of times, maybe it makes no difference. So again, you can think of something like your assignment, your implementation of a game. What difference is it going to make to the player if it takes 0.1 second to execute a move, or 0.2 seconds, right? Or 0.5 seconds even? Probably the player won't even notice. Probably that difference will just drown in the general sort of noise of other stuff that the operating system is doing anyway. So yes, complexity is important, but only when it actually is important, is the message. All right. So the last bit that I wanted to cover through today is about formal grammars. This might look a bit disconnected from the other things, but it does sort of fit together with some of the previous things. So, so what's a formal grammar? Well, to say what a formal grammar is, let's start with what's a formal language. So we talk about programming languages. Java is a programming language, so it's Python and C and all the other ones that you might have heard of or not. But English is also a language, and so is Icelandic and whatever else you might be familiar with. So formal languages are, in some sense, artificial languages. They're languages that have been constructed, whereas what we call as the opposition to formal is natural languages, which are the languages that we use, which have somehow emerged or evolved naturally from human interaction over time. So I guess there are, you might be familiar with, there are also languages for human communication that are artificial in the sense that they are formally constructed. Esperanto, I guess, is the most famous example, although that I'm not sure how precise that one is, but there are other examples of sort of slightly smaller or simpler artificially constructed languages for human communication. There's one called Toki Pona or something like this, I think, which is deliberately designed to be a sort of a limited language that has a very small vocabulary. It's only for talking about sort of simple everyday things. So I don't know to what extent, whether we would call those formal languages or natural languages. But because a formal language is something that is artificially constructed, at least in the mathematical sense or in the computer science sense, a formal language is also precise. So it is not just an artificially constructed language, but it's a language that is very precisely defined. So we have specified somehow exactly what is the syntax of this language. We might also have specified the meaning, but typically here we're only talking about the syntax. And typically we use a formal grammar is the mechanism that we use to define the syntax of a formal language. So again, if you have done or are doing or are going to do courses on the theory of computation, you will also see you will see that formal languages are very important in the theory of computation. And grammars is one way we use to specify them. The other alternative is what's sometimes called an accepting machine. So a grammar sort of defines all the things that all the sentences or expressions that are correct according to the formal language or syntactically correct. An accepting machine is some kind of theoretical machine or algorithm that for a given input determines if it is in the language or not. So it's like an oracle, is often called. It's a function that will classify all possible strings or inputs as either being syntactically correct or not correct. So that's a different way of defining the syntax of a language. But here we'll only talk about grammars. So these formal grammars are often also called generative grammars because, and the reason why they're called generative grammars is because the way that we define a language using a generative grammar is essentially the last bit on the slide here. The language is the set of all terminal strings, and I'll come back to in a second what that means, that can be generated using the rules of this grammar. So the grammar generates all possible expressions or statements or whatever we want to call them that are in the formal language. So generative grammars can look a bit different, but typically they consist of a set of terminal symbols which sort of are the words of the language. So instead the language will be all strings or sequences that consist only of terminal symbols that we can generate using the grammar. And then we have a set of non-terminal symbols which correspond to somehow intermediate steps in this generation of a sequence of terminal symbols. And you can think of as an analogy when we describe the grammar of natural languages, we have names for certain things. We have phrases and clauses and subjunctive clauses and noun phrases and all these things, right? Prepositional phrases and whatnot. So the non-terminal symbols are kind of the analog of those concepts in natural language. So they correspond to certain parts of expressions or sentences. And then we have the core of the grammar, which is a set of production rules. And a production rule has a left-hand side and a right-hand side. And on the left-hand side, we have either just one symbol or some set of symbols. And on the right-hand side, we have another set of symbols, or not set, sequence of symbols. And what the production rule says is that everywhere where the left-hand side occurs, we can replace it with the right-hand side in an expression. So in most of the grammars, well, all of the grammars we will see today, and most of the grammars that you will ever see probably, the left-hand side is just a single non-terminal symbol. So it's just saying everywhere where we have this particular non-terminal symbols, one of the possible ways that we can sort of expand that non-terminal is by putting this sequence of symbols instead. And this process is recursive because the right-hand side can also contain non-terminal symbols, even the same non-terminal symbol as the left-hand side, so we can have recursion. And then finally we have to say what we're starting from. So we have something that is a specified starting symbol, which is saying that we start with this non-terminal symbol and then we apply whatever rules we want anywhere where they are applicable until we get to some string that contains only terminal symbols. Then that is a string that belongs to the language. So let me just skip that for a sec and jump back to it and demonstrate with this little example. So here's sort of a naive attempt to apply this idea of formal grammar to English. Right? So as I said, we have a starting symbol, sentence, let's say, which is supposed to describe a whole sentence, and it's saying that, you know, a sentence consists of a noun phrase followed by a verb phrase followed by and I'll go back and explain this syntax in a moment, optionally another noun phrase, right? And then the example here is just showing this process of derivation. It's saying that, okay, a sentence can be decomposed into a noun phrase followed by a verb phrase. Okay, so we apply that production. Now we have a noun phrase followed by a verb phrase. And then recursively, if you want, we apply some production rule to say that, well, a noun phrase can consist of an article followed by a noun. Okay, so we apply that rule and turn this noun phrase into an article followed by a noun. And then we have somewhere we have a rule that says, another production rule saying that article can be one of these. So we take one of them and put it in there. And now this here is a terminal symbol. So we can't do any more rewrites on that. And we do the same, and in the end we get a sentence. All right, so let me jump back to this one, Backus-Naur form. So what's called Backus-Naur form, or extended Backus-Naur form, or EBNF, is a sort of standard way of representing a generative grammar. I put standard in quotes because it's not particularly standard. There's a lot of variation in how these things are written, but the idea is that we sort of come up with a syntax for writing these formal grammars, which means that we can take these formal grammars and input them into programs, which can parse them and do things with them. In particular, we can write down a formal grammar, input into a program that will generate a parser that will parse strings according to the grammar, which is called a parser generator. We'll look at an example of this. So the EBNF, or extended Backus-Naur form, has a bit of what we might call syntactic sugar. So it has a few extra constructs that just makes it easier to write grammars more compactly than would otherwise be the case. So you don't have to have all of these things in a language for formal grammars. You can sort of get away with having basically just production rules, right? Of course, you need something to identify your terminals and non-terminals, but the the key things that we have here is this vertical bar, also often called the pipe symbol, is used to represent alternatives. So coming back to our example here, for example, an article can be either the terminal string a, or an, or the, right? So the vertical bar represents alternatives. Choose one of these. The other thing we have here is the curly braces and square brackets, and an expression in curly braces is something that may occur 0 or more times. So it's saying this is like a while loop, right? You have a repetition. Again, yeah, okay. Do we have any? We don't have any in here. Okay. The square brackets represent optional elements. So that's something that can occur 0 or once. So this is saying that optionally you are allowed to insert something here, but you don't have to. So that we have some examples of here. So in the first production rule, we said that a sentence consists of a noun phrase followed by a verb phrase, and optionally followed by another noun phrase. So we can have, essentially this is just a way of saying writing two different production rules in a more compact way. So we could just write multiple production rules instead of doing this. All right. Now, I didn't mention this at the beginning here, but the sort of concept of formal grammars was invented, I think, well, Chomsky is the one who's often credited with having invented it, and he was studying natural language, and he was looking for ways of describing natural language, and in particular of describing different complexities of natural language. And there is a hierarchy of different sort of more or less complex formal languages that can be defined by more or less complex grammars or types of grammars. But again, this is something that you will see if you take any of the courses on theory of computation. So the problem with applying something like a formal grammar to a natural language like English is that it's very hard to actually write one that is correct, in the sense that most of the time what you end up with is a grammar that over-generates, what you might call. So the one that we have written here can give us some correct sentences, like the first two are fine here, but it can also give us, well, sentences that are not even grammatically correct. So this is what we might call over-generation. So the blue yellow horse talked the we. So here this grammar allows us to insert an article in front of every adjective or noun that we have in the sentence, which of course in actual grammar we can't do. But even if we were to sort of fix this and write a really complicated grammar that gets rid of, well, we couldn't get rid of all of it, but most of this, we still have to remember that a formal grammar only defines syntax. So the last one, which is a slight variation of a famous example, is that we can always, with a formal grammar, construct syntactically correct sentences that are typically not meaningful. It depends on what exactly is the language that we're describing, but you always have sort of the formal grammar only defines syntax. It doesn't define meaning. So in some cases you might have a language where actually every syntactically correct sentence or expression has a meaning, but in most cases you wouldn't. So again, if you think of programming languages, you can easily write syntactically correct Java that is meaningless, right? That is semantically incorrect, that applies, say, operations that are methods that are not defined, or applies them to values of the wrong type, or uses undeclared variables, and so on. So all of these things are, in some sense, syntactically correct. They follow the language, the format of the language, but they are not meaningful. So they don't have semantics. So again, the point here is just that formal grammars define what is correct syntax, not what is correct semantics, or not at all what is the semantics. So I wanted to illustrate this, both to illustrate what these grammars might look like, but also sort of illustrate why you might care about them. But instead of looking at the slide, let's have a look at an encoding of this here. Now I couldn't completely make this example work. I'll explain in a moment what's wrong with it, or well, what I couldn't figure out, and then see if you can figure it out. So I mentioned before that by having a syntax where we can write down formal grammars, this allows us to give the formal grammars as input to a program, which can do something with it. For example, generate code that will parse inputs according to the grammar. So this is an example of the input for one of these parser generators. This is for Antler, ANTLR, which is, I think, the most commonly used one for Java. This and also this is the reason why I put standard in quotes there, because here, if you look carefully, you can see that the syntax that they use here is not exactly what was in the extended Backus-Naur form, so it's slightly different. But the concepts are the same. I'll show some of the differences here. So in the EBNF, we used square brackets for optional elements. So here what they're using for optional elements is a question mark. So let's just look at, for example, the first production rule here, saying that a real number can be either an integer or, so we use the vertical bar for option, or so not option, choice or alternatives. Okay, so that's the same. Parentheses are just used for grouping, so same as when you write, arithmetic expressions, you put parentheses in order to show that these things are a group, and also to deal with sort of disambiguating what might otherwise be ambiguous expressions, right? So this is saying a real number is either an integer or it's something that matches this, right? And here, this is saying that we can have a start with a minus sign, and then there's a question mark here after the minus sign, and that's saying that the minus sign is optional. So if we were to write this in, actually, let's see if we can. I don't know if they have a comment syntax here. I think it's like this. It doesn't matter anyway. We're not going to run this. So if we were to write this in EBNF, actually there's another difference. EBNF says that use equal sign between the left and right hand side of a production rule. Antler uses colon. So instead of this question mark here, we would put square brackets. And then after the optional minus sign comes a natural number. So that's a non-negative integer. And then comes a dot. And then comes some number of digits. And again, here's the difference. So we said that EBNF, we have curly braces for repetition. But here they're using a star. So it's saying that digit star means 0 or more digits, right? Or 0 or more strings that are generated from the non-terminal symbol digit. So if we were to write this in EBNF, we would have, instead of the star, we would have square braces, or sorry, curly braces here. And then comes a non-zero digit. So this is saying that we're not allowed to write here real numbers that have an arbitrary number of trailing zeros. They have to end with a significant digit. And then there should be an end of file here, which is just saying that the that should be all of the input. So in what you can see here is that apart from these sort of syntactic differences, these match the examples that are on the slide here, if you want to come back and look at those later. But you can sort of see this is not exactly recursive, but we define different non-terminals in terms of other non-terminals here. So we're saying that a real number can be either an integer or this expression, which includes natural numbers, digits, and non-zero digits. And these are all non-terminal symbols. So we have other production rules then that say that an integer can either consist of a 0 or an optional minus sign followed by a non-zero digit followed by any number of digits, 0 or more. And the reason why it has this construction is we want to disallow writing -0. So -0 should not be a valid integer. At least that's the intent here. Natural number similarly can be either a 0 or a non-zero digit followed by some number of digits. So again, we don't want to have any leading zeros here. So we're saying that 0, 0, 0 is not a natural number. If it's 0, then only one 0. Or 0, 0, 1 is also not a natural number. It has to be written as just 1. And then we have just the definitions of the character classes here saying that non-zero digits are 1 through 9 and 0 is just 0, right? So we can put this through, as I said, a parser generator. The parser generator spits out in this case actually 2 Java classes, which are called the parser and the lexer. They're pretty they're not code you want to read because they're auto-generated and they're not particularly readable. But we can try using them and we can try parsing something. So So here is just a simple example where we just parse an integer. The actual procedure for parsing an integer is a bit more complicated here, but essentially it's turning this string into a stream of tokens, and then wrapping a parser around it, and then we call parser.integer here, and we check was there any syntax errors. So that was my idea, and we returned that as a boolean. So this should then tell us if this is an integer or not. So we can attempt to run this. And this returns true. Now, and if we put something different here, something that is definitely not an integer, like that might be an integer in Latin, but it's not an integer according to our grammar. So if we run this, it returns false. Now the problem I was having with this thing is that I can't get it to report errors in a usable fashion. Actually, let's see what it does with -0, because we said that we had written the grammar to exclude. Okay, so it's saying that -0 gives us a false. That's good. But let's say I write something like this. So I write a large integer and I use commas to separate the thousands. Now, according to the grammar that we have written, this should not be a valid integer. But I think if we run this, it's going to return true. So, and I haven't been able to figure this out. So you can see that it prints out error messages saying that this is not allowed, or saying that when it encounters the comma, saying that I can't parse this. But then in the end, it doesn't return any parse errors. And I have not been able to figure out the interface of this generated parser and how to make it always actually report the errors in a way that I can use programmatically. So probably this is available somewhere in the documentation, but all right. So that's the end of that, and we're very much at the end of the lecture time. So I said this was a bit of a mixed bag, might have been quite a lot. If you have any questions about it, of course you can come back and ask by either after the lecture or via Piazza or something like this. All right, that's all. Hang on.